Hi everyone, my name is Ranjan. Today I'm excited to present my final project, IoT-enabled smart irrigation system based on soil moisture monitoring. Let's start with a problem. We live in a world facing rapid population growth and climate change. These global challenges demand high efficiency and sustainability in agriculture. However, traditional irrigation methods still rely heavily on human experiences. This leads to inaccurate and delayed watering schedules. There are three major pain points right now. First, under irrigation. Second, over irrigation. Third, and perhaps most critically, the lack of digitalization. Farmers have no access to real time soil data, nor any way to remotely control irrigation for active management is basically impossible. So the question is, how can we use IoT technology to solve these problems? That's exactly what my project addresses. Before designing the system, I looked into exciting research to key papers for this work. Inspired by these findings, my solution is a closed-loop smart irrigation system. It continuously monitors soil moisture in real time. When moisture drops below a scientific threshold, the system automatically turns on the water pump. When it rises to an optimal level, it shuts off. Importantly, I designed a dual control mechanism. The system runs local edge control for automatic operation, but also supports remote manual override via cloud. And all of this is integrated with SceneSpot for data visualization, trend analysis, and alert notification. Now let's look at the system architecture. I followed a standard IoT four-layer model. At the bottom, the perception layer includes the ESP32 microcontroller, the soil moisture sensor, and the water pump actuator. This is where physical data is collected and the immediate control happens. Above that, the network layer uses MQTT over Wi-Fi. MQTT is a highlight, publish, subscribe protocol perfect for resource-contained devices. It handles two-way communication, telemetry data going up, and the control commands coming down. Then comes the platform layer, ThinkSpot Cloud. ThinkSpot manages device registration, stores all time series telemetry, runs the rule engine for alarms, and renders dashboards. Finally, at the top, the application layer provides the user interface. Farmers can access the dashboard from a PC or mobile browser to see real-time data and manually override the prompt. Alarm notifications are pushed visually on the dashboard. This layered design ensures clear separation of concerns and makes the system scalable. You can add more sensors or fields without changing the core logic. Let's move to the experiment setup. For the soil moisture sensor, I used a potentiometer to simulate the sensor in the walkway environment. It output a 0 to 3.3 volt analog signal, which is read by the ESP32 ADC on GPIO34. This value is then mapped linearly to a 0 to 100% moisture scale. The principle is electrically identical to a real soil moisture sensor. The only difference is the physical component. For the water pump actuator, I used a simple LED connector to GPIO2. When the LED is on, it indicates the pump is running. In a real development, this LED would be replaced by a relay module driving an actual water pump. The control logic, however, remains exactly the same. This prototyping approach lets me validate the full control loop without needing physical hardware, ensuring the system works before any field installation. On the software side, the data processing is quite comprehensive. The sensor is sampled every 2 seconds, providing near real-time monitoring. The core control logic uses a hysteresis control algorithm. If moisture falls below 30%, the pump turns on. If it rises above 70%, the pump turns off. The gap between the 30 and the 70% is a hysteresis band that prevents the pump from oscillating on and off at boundary conditions. Beyond thresholding, I implemented change prediction using Edge AI, which I will explain in a moment. All communication uses MQTT. It's a highlight, publish, subscribe protocol that significantly reduces CPU usage and transmission time compared to HTTP, making it ideal here. It natively supports bidirectional communication over a single connection, enabling seamless real-time telemetry upload and remote device control through the ThinkSpot platform. This is the backbone of the health system's connectivity. Let's dive deeper into the dual layer control method, which I think is a highlight of this project. In a local auto mode, the ESP32 makes decisions independently. This local logic can run even without internet, making the system reliable in field conditions. In the remote manual mode, the user can directly toggle the pump from the ThinkSpot dashboard using a switch. This sends an RPC command over MQTT, for example, a method called setPump. With parameter state2, the ESP state2 receives the command and overrides the local logic. The priority rule is clear. Remote commands always override local automation. If a farmer manually turns on the pump from a mobile phone, the system holds that state until the farmer releases. This ensures human control for a real-world scenario. The flowchart on the slide illustrates the complete decision logic from sensor reading to final MQTT publishing. Now I want to highlight two advanced capabilities, Edge AI and cloud computing. For Edge AI, I implemented a simple yet effective change prediction algorithm. Every 5 seconds, the ESP32 calculates the moisture change rate if a rapid drop is detected. For instance, moisture decreasing by more than 2% in 5 seconds while still in the 3250 buffer zone. The system proactively turns on the pump before the critical load threshold is reached. This prevents cross stress during fast drying conditions. The decision runs entirely on the ESP32, so it remains operational even when cloud connectivity is lost. That's true edge intelligence. Additionally, the cloud lays a foundation for future enhancements like big data analytics, long-term pattern learning, and more complex AI model training. Um, about another key feature is mobile computing. You can see this employers, farmers with on the go ubiquitous control, whether at home or in the field. They can always have visibility and the control over their irrigation system. Um, Now let's go to the results and performance. Um, this screenshot shows the integrated system in action on the left side. You can see the Valkyrie simulation running the serial monitor confirms successful Wi-Fi and MQTT connection, and data is being published every 2 seconds. On the right side, the ThinkSpot dashboard displays the real-time moisture value pump status card and the historical change chart, checking that matrix over time. During testing, I verified several performance indicators, and you can see here is the video, and the video is relatively long, so I will post a link. And now I don't want to show the full video. Um, but the data upload success rate was 100% in the simulation environment, and the control command latency was under 1 second. The Edge AI proactively detected fast drying conditions, as you can see in the serial output. Fast drying detected, pre-watering activated. The cloud alarm directly triggered when moisture went below to 25%, and the alarm which appeared on the dashboard immediately. The results demonstrate that the prototype successfully integrates hardware simulation, reliable communication, drive layer control, edge intelligence, and the cloud-based monitoring into a coherent working system. That concludes my uh, presentation. The demo video link and the project workshop link are attached on this slide. Thank you for your listening.